Can people on Zoom hear me? Okay, cool. Okay, so what I just said was we're going to start off by just starting the installation. So you have two options. You can either do the Colab or the Docker container. The Colab is better if you want to do the deep learning part, because it's faster because it has GPUs. The Docker is better if you want to do the symbolic regression part, but you could also do both. So the Docker part, if you've ever set up Docker before, you can download the Docker desktop here. This is essentially just a way to have a reproducible build. So I don't need to walk you through kind of how to set up the Julia Python interface. But you can also do the Colab. The Colab is kind of automatic, so we don't have to talk about that now. But if you want to do the Docker, you're going to want to download Docker desktop and then go to this link on GitHub, Miles Cranmer / Piser_tutorial. And on that link, what you're going to do, so if I go to downloads, I'm going to clone that repository, go into that repository, and then you follow the instructions. So the first command is docker build t Piser. Feel free to just say if anything is going wrong, and I'm happy to help. So once you download the repo, just hit docker build. So I already installed mine, but it might take yours a bit longer. Okay. So while that is building, I can do the talk. It depends how fast the internet connection is. It shouldn't take too long. It should only take like 10 minutes. But I think it's just easier if we do it now. Okay, so so I'm going to talk about kind of what I see as a problem for machine learning in the sciences, which is that there's a lack of interpretability. And so I'm not a deep learning skeptic. I actually do a lot of deep learning research, but I'm going to explain how I think we can make machine learning more robust for the sciences. So I'll start off by just asking, okay, why do we actually need to interpret machine learning? I think machine learning, I think it is going to, I mean, I think there's so many problems in the sciences that it can help solve. So one of the nice examples of this is the protein folding problem, which was pretty much solved by DeepMind. So this is a 5-decade problem in biochemistry, going from a amino acid sequence into a protein structure. People can solve it for 5 decades. Deep learning comes along and can get very accurate predictions. I think we'll see more and more examples like this going forward. But the big problem I have with these kind of approaches is there's no scientific insight. So Einstein created general relativity from maybe only like a few empirically backed postulates, just a few ideas. He was able to derive this very general, powerful framework for making predictions about gravity. And that's still used to this day to make predictions about the event horizon of black holes. Where on the other hand, if I train some machine learning model on some data set and I slightly perturb the training examples, it can completely throw off the model. And I think that's something that machine learning really needs to address for it to be more useful in the sciences. I'm going to skip through these. This is like the machine learning introduction. So I think a really nice example of this, well, a scary example. There was a paper in 2016 on detecting pneumonia in hospital patients. And it was claimed that the neural networks were better than physicians at detecting pneumonia. It turned out the neural network was not looking at the lungs at all. It was actually looking in the background of the image. There was like this text that was basically correlated with the diagnosis, and it was just reading the diagnosis. So, I mean, I think neural networks, they're really good at cheating and kind of finding shortcuts in the data that you didn't even realize existed. And I think this is hugely problematic for sciences, especially when we train a model on simulated data and then apply to real world data. we might not realize there's artifacts. Yeah. I think so. Yeah. So I think it's better than one doctor, but it's worse than like 5 doctors in consensus. I think that's how they get superhuman performance. Yeah. Or maybe they take additional scans to get better predictions. Yeah. But it was claimed to be better. So if you look at the history of science, a lot of the time when we make a new scientific framework, it follows this pattern where you make an empirical observation. So maybe Kepler's third law describes the relationship between the period of a planet's orbit and its radius from the sun, a semi-major axis. So that is what inspired Newton's law of gravitation rather than an apple. Planck's law, which is found in quantum mechanics, this is actually another one. This is a function fit to data. And it would partially explain, or quantum mechanics was developed partially to explain that. Whereas if I have this knowledge trapped inside a neural network, and I don't know what the weights are really kind of saying, there's not much I can do with science. So science is kind of like at a dead end, unless we can get something out of the network. So this is a paper we had in iClear. So this is led by Kim Stockenfield at DeepMind. We essentially looked at, I don't know why it's not showing the title. Oh, that's weird. Okay. Okay. We have this turbulent box here. So it's just a fluid in a box. You coarsen it. So you reduce the resolution and you rerun the simulator. Then you let a neural network learn a simulator to also run in this kind of blurry version. And it can do better, and it can do much better, kind of like it has a better bang for its buck in terms of resolution. So you actually get 1,000 times speed up when you run fluid simulations. The problem with this, when we were writing this paper, is we didn't really understand how the model actually achieved this. Like, what is the scientific insight that can help us develop our understanding of turbulence? Because I think that's what you really need to do to get strong generalization to other parameter spaces. So I'm going to skip some of this. Skip this. So, okay, so the way industry does interpretability, which I think is kind of, I think it's good for vision and language. It's called the saliency maps, if you've heard of this, or like Shapley values. These ideas tell you kind of what the network is looking at or what it's sensitive to. So if I have this image classifier that's trained to detect lions and dogs, I can take the gradient of my learned model F with respect to its inputs, and that gives me kind of a sensitivity map, and it tells me what the network is looking at. But I think the problem with this is that in science, we already have a modeling language that's really good, and that is mathematics. Whereas in computer vision, you don't really have this rigorous framework. So I think when we do interpretations of neural networks, I really think it's good to map it to our existing language. So that's my kind of argument for interpretability. And you can look at like a physics 101 cheat sheet, and it's all simple equations, and they're all really good. So I think this is a powerful prior for physical models, and we should try to exploit it. So we should distill kind of learn models into the language of science, which is math. Let's skip these. So what I'm going to teach you today is this technique called symbolic regression. Symbolic regression is essentially finding analytic expressions that fit a data set. So rather than having some massive over-parameterized model and tuning parameters, you're going to arrange symbols until the evaluation of that tree matches some relationship in a data or otherwise optimizes a function. So the way you would do this is you have some symbols, so like a plus, cosine, x variable, y variable, and some data set, maybe you run a genetic algorithm typically to arrange these symbols until you find this equation. So what I'm going to teach you today is it's called Piser. So it's Python symbolic regression. It's the Python side is the front end, and there's Julia backend to it, which is actually where the genetic algorithm is. It's an open source symbolic regression library. It's compatible with scikit-learn machine learning library. You can do distributed compute. If you have a lot of cores, you can distribute it over a cluster, and you can define like custom operators, losses, constraints. So it's kind of a very flexible tool that I made because I wanted to use this, and the open source tools out there were kind of either too slow or they cost a lot of money. So I'll teach this today. So the way Piser works, you represent every equation as a tree of operators. So like a plus operator, multiplication operator, whatever operator you want, that is equivalent to that equation. And it's also equivalent to this evaluated over your data set. The way you move around in this space is like you don't have fixed scalars to kind of do gradients on. So the way we do it with genetic algorithms is we have these different genetic operators. So a mutation is one operator. So maybe I have like a plus operator and I change it into a minus. So there's different like maybe change a sine into a cosine. Maybe I kind of randomly add a tree somewhere. Maybe I kind of perturb one of these constants. These are all different ways to explore the local space of equations. You can also do crossbreeding. So if I have two equations, which are pretty good but not perfect, I can like pull ideas from evolution and just cross over part of their genetic code, which is the tree. And so maybe I do that, I swap that expression and this one, and I get these outputs, and one of them maybe is a good match. So this idea is actually really powerful. Just so mutations alone don't really get you too far, and you kind of end up in local minima. But actually breeding equations together is a really powerful way of exploring the space, because it kind of lets you take abstractions that appear in many different equations and kind of pass them around. So maybe one sub-expression you learn is like x squared plus y squared, and then you start breeding equations and it kind of ends up in different places. So this is actually really important feature of Piser. So I'm going to get into a little bit of technical details. So the way parallelism works here, it's based on this idea called tournament selection. So I have different populations of equations. So at any given time, I have maybe like 10,000 equations, and they're split into groups where each group of equations, you can kind of think of it as an island of equations where they kind of evolve into their own species. The reason it's partitioned like this is due to just to make it possible to parallelize. So I'm going to have different groups sitting on different cores. I run evolution for a number of generations, and then I do a migration. So maybe I take the best subpopulation from one island, and I maybe move it to another and swap those ones. And this is kind of how you introduce more equation diversity between islands. So this is basically just like an engineering trick to get to allow you to use like 1,000 cores to do a search more efficiently. So this is, yeah. Good question. So you define a fitness function that could be, I mean, it could be like any optimization objective. If we're doing regression, it would typically be like the mean squared error with respect to my data set. That would be the fitness. You could also add in a complexity penalty as well. Yeah, so typically it's actually hard to overfit in symbolic regression because your search space is so small. So typically overfitting is like something you'd see in traditional machine learning algorithms where they're very, very flexible and they have this massive function space. But symbolic regression actually has a pretty small function space. unless you kind of allow the complexity to be really, really massive. So you usually don't have to worry about overfitting. However, it does happen sometimes, especially with like very small data sets. And there, the complexity penalty is kind of what regularizes the space of equations to prevent overfitting. But like another thing you could do is just do cross-validation afterwards and kind of compare it on a test set. Yeah. Yeah, great question. So this is the loop. So you have this population of equations. So this is like one island. Okay, this is one island. Then I'm going to use an algorithm called tournament selection. This is a classic algorithm. I think it was developed in like the 80s. It's not new. Piser adds like a couple little tweaks, but the overall algorithm is an old idea. So you take this population, randomly choose some. So maybe you have like 100 equations, you choose 2. Randomly choose 2 equations. So I have x to the power of x, 1.15y plus 0.86. So of those, I compute a fitness function. So maybe it's a regression objective if I'm trying to like match a data set. Maybe I have a complexity penalty, like you could, like any optimization objective would be my fitness. Then I take the fittest of that subset. That's kind of like the winner of the tournament. And then I go through a random pathway. So maybe I do a mutation, maybe I do a simplification, like an algebraic simplification, or I could do optimization on the constants. So what I found is that, and this is also kind of an old idea, is genetic operators are not really suited to optimizing constants. It's actually better to do local, what's called a local leaf search. So you just tune the leaves of the tree. And I do it randomly. Yeah, all of these are basically like different random perturbations to my population. Crossover again. So crossover would be like top 2 equations. So all of this is implemented on the Julia side, and the Python is kind of like a wrapper to give you the output. But yeah, these techniques let you explore the space of equations efficiently. So yeah. It's gradient descent. So you can choose different optimization objectives. So it uses the optim.jl Julia package. And so the default is BFGS. You could also use Nelder-Mead or like Newton's method or something else. So Piser does actually compute like the symbolic gradients, but you can also turn those off. Like if you have discontinuous operators, you might want to just let BFGS figure it out and not worry about the like exact gradients, especially like if you're doing mini batching or something. Yeah, good question. Any other questions? I'm happy to take questions later on too, if you think of one. Yeah. So actually this part, I don't parallelize. This is sequential. So the parallelism happens at a subpopulation level. And so each island would like sit on a core. So I've thought about like other ways to parallelize it. I mean, you could kind of pre-split it into subsamples and then run tournament, but actually it doesn't help you that much because you've already split up the population in so many different subpopulations. It's like, it's already saturated. So the extra parallelism would be like more threads than cores, typically. Yeah. And you can also parallelize the evaluation, of course, of a single equation over a batch. Yeah.
So like, okay, so I think like the idea to parallelize would be each of the samples in the population in the airways. So that's not quite the use this with subpopulation. Why is that?
So why do we split into subpopulations?
On the population. Yeah. So sending each individual population.
Okay, so the way evaluation works is since you're only changing one equation per generation, you can just save the losses from the previous generation for like all of them except one. And then when you have a new one, you just evaluate the loss really quickly. Yeah, but the parallelism, like this is enough to saturate it by just splitting it up into groups of like 100 equations each. Yeah. Yeah. Mhm. What is a population data set?
I mean, like you define a distribution.
Oh, no, we don't, but that's a cool idea. No, we don't. It's just a finite data set, but you could do that. That sounds interesting.
If the final model approximates the going closer to generalize all kinds of people.
Yeah, you would hope. Yeah, I mean the neural network. I'll come to the neural network later.
Or any.
Yeah.
Can be any other language that
Yeah. Right. Yeah. So the data set, it's typically like you assume it's. I mean, you're doing empirical risk estimation. So you're assuming that you have enough samples that you approximate like the true distribution loss. Does that satisfy? No? Okay.
Yeah. There's like why
Oh, you would at the end. You could have a validation set and just not train on that and then validate at the end. But it's not, there's no validation set in the loop. Yeah, the validation set, it would come after, like if you're testing the equations rather than in the loop. Yeah, I mean, I think that would be a good idea in the future to have like an inner validation loop. Because like sometimes you're doing constant optimization. So it might be good to kind of like only optimize constants on like a subset of the data. That could be a good idea, actually. Yeah. Yeah. Okay. Right now, so the backend can handle anything, but right now, SymbolicRegression.jl is only scalar functions. You can pass it multiple outputs, and it'll fit multiple scalar equations, but it won't search for vector equations. I mean, there's the tricky part about vector equations is like, you would typically have like mixed types in the evaluation. Like some of the types would be vectors and then they would go into scalar operations. And so it's tricky because genetic operations, like you want it to be like one step to the next equation and you don't want their loss to be too different. But if you are starting to work with like different types, some of those trees are going to be like invalid because like you introduce a new vector operator, but it goes into a scalar operator before introducing another vector that makes it a scalar. So it's like, it's really hard to search that space. I think, I think that's a nice part about Julia. You can have multiple dispatch and like have different type definitions for each operator. So I think that could be something cool to exploit in the future. Like you could have like a dot product that is defined for vectors and for scalars. Yeah, I mean, I haven't really explored that yet, but it should be able to handle it. Yeah. I'll just talk about performance a bit. So yeah, maybe we could go through this and then I'm just thinking about timing. Okay, yeah, let's talk about this. So like searching for equations, it's very evaluation intensive. So if you're training a neural network, you maybe have to do 1 million evaluations, like 1 million gradient steps, order of magnitude. But for symbolic regression, you want to do like 1 billion evaluations or more. Like if you want a converged complex equation, you really want to do as many evaluations as possible. So much of the performance is just about how fast you can evaluate an equation. So that's why I started using Julia, because I don't want to write something in C because I don't want to like spend 10 years writing a C library. I've used C before and it just takes time. But so that's why I wrote it in Julia. So I kind of treat Julia like a C backend to a Python library, but it's like faster to edit. So how can we make evaluation fast? So this is like some actual code demos. So this is like the internals. We're gonna do a Python, but this is like the Julia internals. So each equation is a binary tree. You have a single struct that is like fixed size for every node of the tree. Basically, every operator, so the user will define a set of operators, then those are used to define an enum. So a node of the tree will store like a 1 for a plus, a 2 for a minus, 3 for multiplication, right? So it's a very lightweight tree. They're not actually storing functions. And that's important because you want to quickly generate trees. All the types are fixed. So like this would store the type of the tree. So if it's like a complex equation, you would have a complex type there. And then it would also store like, okay, if this is a feature of the data, what feature is it? Now the part that makes evaluation fast is basically the entire backend gets recompiled whenever you change the operators because it's building this enum. So the search options are a type defined by the operators. So whenever the operators change, your type changes. And that makes the whole library recompile to those specific operators. And that's kind of why you get fast evaluation. So the way the evaluation works is, this is like a call for a 1-degree operator. And I pass the index of the operator. And this is basically a type. So this function gets recompiled every single time you define new operators. And basically what that means is when this function gets compiled, it knows what operators it has. And so because of that, you can start to do things like fusing operators together to get really fast evaluation. So since all combinations of operators are known beforehand, you can fuse operators. So this is a single simmed kernel of 2 unary operators. So maybe I define my operators as like a cosine and a square and an exponent. Because I've set it up in this way where the type defines the operators, it's going to compile a new simmed kernel for every single combination of operators. And this gives you a really big speed up because it's just going to look up, okay, what function do I need to evaluate this sub-expression? And it just goes right to a simmed kernel that is like pre-compiled, and it's just really fast. So this is like I think the reason Piser is a really good library is maybe not because like the algorithm is smart. It's just like it's optimized to hell. And I think that's why like it's pretty good at searching. So this is what a Piser call looks like. So if you've used scikit-learn before, there's these regressor objects. So you define a model. It's basically a dictionary of parameters. So I define maybe the number of steps, what operators I want, what my loss function is. Now you'll see here, I'm actually passing Julia code to Python, to my Piser regressor operator, or Piser regressor class. And basically what this is doing, it's letting me define custom operators from Python. So if and like this doesn't even need to be differentiable. They can be like really ugly if statements, but you can define arbitrary operators from Python. And they will be compiled into simmed kernels and be just as fast as if you had like hard coded a C++ library, which is really nice. The whole what piece? So yeah, so it basically does, because like once you do .fit, it just Julia runs. Yeah, so it's pretty fast. Yeah, it doesn't like there's not really like some Python libraries like PyTorch, they kind of go back and forth, but Piser is just goes to Julia, and then when it's done, it returns. Yeah. Just fast. Yeah. Yeah, so it's basically like if you've defined custom operators like a cosine and a square, it's going to build a simmed kernel of those together, like cosine square on like multiple data points at once, cosine square, cosine square. And that gives you like a really nice speed up. Yeah. Okay. So these are the dependencies if you're curious. I don't know how many people have used Julia here. So symbolic regression is like the main search. So this is the back end of Piser. For fast expression evaluation, it uses this submodule called dynamicexpressions.jl. So I kind of split that out into its own library. So that uses loop vectorization.jl for the simmed loop. So those are like really fast. It's like if you've ever used JAX, it's like as fast as JAX for the evaluation. And then it does source to source gradients with the zygote. So if you've defined custom operators, it also compiles the gradients of those operators. You can get really fast derivatives as well, which is useful for gradient descent. And then it uses optim.jl for constant optimization. If you want to do like Slurm, like you have a Slurm cluster and you want to distribute over like 1,000 cores, you can use so there's cluster managers.jl. And then it also does some random simplification in the middle, and that's symbolic utils.jl for that. Okay. Yeah. So those are the main dependencies. And then the front end is Piser. So this goes through PyJulia, which is like Python, but lets you evaluate the Julia runtime. And that basically lets them talk to each other. Okay. I don't know if anybody wants to see that. It's like how it works. Okay, this is a quick demo, and I promise we'll get to code soon. This is like a little IPython notebook. Maybe I create some observed data. Then I create a Piser regressor object. And I'm going to say, I want to search for this many steps. So that's the number of iterations. This is my max complexity. These are my operators. And then I do model.fit on my data. Maybe I define a variable name so it prints out nicely. I run the search. So this is going to dispatch to Julia. Julia does the search itself. So this example is like kind of too simple because it found it and you don't really see it, but it's like, it's a pretty fast search. And then, so this is good, like if you're doing research, you want to put these equations in your table, and maybe like you have like I don't know, you have a conference deadline and you want to like put the equations in your table. So you can generate a LaTeX table of the equations. And then they look pretty. So this is Henrietta Leavitt's law, which describes the relationship between a Cepheid's period and magnitude. Yeah, so how well does this work? Because it is a genetic algorithm. It's not like a sophisticated reinforcement learning algorithm, but so it got second place at this Gecko conference symbolic regression competition. The first place is proprietary software, so it's closed source. You can use it if you want. I think it's worse, but I'm biased. I think it's much worse, actually. You can try it if you don't believe me. Yeah. So Piser finds like much simpler solutions. But the really interesting thing about this competition is the top three, QLattice, Piser, and UDSR, they're all genetic algorithms. There was like this massive large language model, but it's like almost off axis. So it's at the bottom, E2ET. That is like this massive transformer model from Facebook. And I think it's really hard to generalize when you don't know what the equations will be, but genetic algorithms, like they don't need a training set. They just go and try to find it. Yeah. Can you what? Yeah, that's a great idea. So I think UDSR actually does that. So UDSR it's a really nice, so it's also open source. It's really nice. I like their group a lot. They do, I think they have like a reinforcement learning. It like generates a population with a learned generative model, and then it feeds that to a genetic algorithm, which kind of does the optimization. So I think that's a really nice idea. I would like to eventually implement something like that in Piser. Pretty much all my time is just like optimizing the evaluation, which like, I mean, it does, yeah, I think the evaluation is like the most important, but I think those ideas are probably useful going forward. Yeah, okay. Okay, I'm gonna talk about the deep learning symbolic regression stuff a bit, and then we can get to code. So I talked about this idea of like, machine learning is really good at finding things in data sets, but it's not good when you want like a scientific insight. You can use symbolic regression to basically do that. You can get insights out of your model by fitting pieces of them with symbolic regression. So the way this works is you train a neural network normally. So like you train, I don't know, whatever neural network you have, just train it normally, then you're gonna freeze the parameters of the network. So you stop training. Then you record the inputs and outputs. So like you pass in the data set, and you're gonna record the inputs and outputs of the neural network. Basically like you're observing some black box process. Then you literally just feed these input outputs to Piser. And you see, okay, what equations approximate this part of my neural network? Now you may say, okay, like why not do symbolic regression directly? And you could do that, but this strategy becomes useful if this is like a piece of your neural network. So maybe you have this much larger model with like different parts to it, and you want to understand one piece of it. This is where this, I call it symbolic distillation. I think that's where this comes in use. So like if you have a hierarchy of neural networks, like maybe this one creates a summary statistic of like a galaxy, and the other one is like aggregating all of the summary statistics. And you could approximate each piece of it rather than having to do this very expensive symbolic regression search. Because like I said, you want to do 1 billion evaluations. So if your loss function is really expensive, you want to start with neural networks and then do just regression afterwards. I'll mention a couple examples. So this is one I really like. This is some people in economics at Harvard, and they found this. They found this gravity equation for international trade. It's like they ran a graph network on the GDP of different countries, trying to predict, I think, GDP distance between countries, and they try to predict the amount of trade between two countries. And then they distill that graph network to different equations. And so you get like these interaction laws between countries, like modeling the level of trade. So it's cool that it applies to like non-physical problems as well. And you get like these interpretable, I mean, I don't understand what the hell it means, but like it's interpretable to them. So this is a paper I did with Case Wong on gravitational wave population models. It's basically you have this normal population posterior, and we find different analytic expressions for it. The final result is cool because it's like it's very physical. Like you have this power law continuum, which might represent like a background population, and then two Gaussian peaks, which represent like subpopulations. I mean, like you could argue you could see that from the data, but when you add more features, I think this is where the symbolic side really starts to help you interpret the data. Okay. So I think in the original paper, I don't know like the classification of the symmetries, but like the networks in this paper are translationally and rotationally equivariant, I think, or they might just be translationally. But in the other paper I'll describe, we did do it with like full rotational equivariance as well. So in this paper, we showed that if you train a graph network with a specific type of sparsity regularization, it actually finds the correct physics. And you can actually like extract the physics that it's learned. Whereas if you don't train with that regularization, it basically just learns like some interpolation scheme, which is cool.
So I wonder to get results like this, what's it compute? For example, if I want to apply something like this, what's a compute budget actually?
Compute budget? Yeah. I mean, it's pretty light. So we'll do one today. Like an example of like neural network distillation. We'll do one later. It's pretty fast. It's like, I mean, it really depends on the problem. Like a graph network like this, you could train it in like 20 minutes on a GPU. And then the distillation, maybe like another 20 minutes. So it's pretty fast. Yeah, so that's like, so that's more for like this. So this equation is like really nasty because you're searching with if statements and Gaussians and like a bunch of other crap. And the data set is like really kind of noisy. So you give it a lot more data. So that's where you want like 1,000 nodes. But for more simpler equations, you can work with like a laptop. Yeah. No, because so evolutionary algorithms are like, they don't really converge. What can happen is you're searching for like days and it seems like it's converged. And then like one population member just unlocks a new evolutionary pathway. And then it just starts exploring from there. Yeah, I think evolution just doesn't seem to converge as nicely as like other machine learning algorithms. Yeah. What I usually do to see if something's converged is I'll just run 2 searches and then stop them. And if they find the same equation, I know they're converged. And it's also good to like mess around with different settings and see if it always finds the same equation. But again, like it might just not have found the minima yet. Yeah. Yeah. Yeah, totally. Yeah. Yeah. But this one? Yeah, so you predefine the operators. You predefine the language. And you actually want to do that because, so I view symbolic regression as like an interpretability mechanism. For it to be interpretable to you, you want it to be in your language. That language is kind of what existing theory looks like. If existing theory never uses Bezel functions, you should not have a Bezel function in your language because you can't really make a connection with your existing theory. Does that make sense? Okay. The path? Like the family tree? Yeah, you can get, there's this one feature that lets you get the family tree. Yeah, it really depends on the complexity. Like some of them, it might get them pretty quickly. Some of them, it might take a while. Yeah. Okay, so this is the last example. So this was a paper led by Pablo Lemos. We wanted to see, can we find Newton's law of gravity just by observing the solar system? So just from the dynamics of planets and moons, can you find Newton's law of gravity? Now, the really tricky part about this is you don't know the masses. Okay, like how can you even find Newton's law of gravity without the masses? So what you have to do is simultaneously learn the function, the force law, and properties of the system. So you're literally like doing gradient descent on the properties of the system, like the unknown properties, and the force law. So it looks like this. So you know the position of each planet, you know the acceleration of each planet, then you're going to assign a random parameter to each planet. So maybe you initialize the masses at like 1 for each planet. Then you say, this is my force law. My force law takes in the displacement between 2 planets and the 2 parameters, which I don't know, but I'm going to try to find those. So this is my law, and I'm cheating a bit, but you have to cheat. I can explain why. So I'm saying the acceleration is the sum over the force law with each planet, right? But I don't know what that force law is. I just know it takes in those arguments, so the displacement and then the 2 mass parameters. I sum that, and then I divide by the receiving body's mass. So I cheat and I say like 1 over the receiving body's mass. You have to do that, otherwise there's a functional degeneracy. So I think it's okay. Okay, so we say F is a neural network, and we're just going to optimize it. So optimize the masses and F simultaneously. Okay. So we use NASA's Horizons ephemeris data for training. We give it, so there's like, this data set is like, it literally has like 500,000 bodies. So we only give it 31 bodies because it's like, we need to actually run it, which is 465 edges, so still a lot. 10 to the 18, so every moon with above 10 to the 18 kilograms, we give it. So it's like 31 bodies in total. 30 years of dynamics, okay? So this is what the first iteration looks like. I spent way too long making this in Blender. I hope you appreciate it. So you can see like the wireframe is kind of like, that's the prediction. The colored body is the truth. And you can see like, okay, it gets the overall dynamics. It kind of looks correct, but the error is like really bad, I think. Like the inner planet is like really bad. So now what we do is we use this new interpretability technique and we look at the inputs and outputs of F. And now we can actually interpret this with our symbolic regression. This is what we get. So what I'm showing here is the complexity of the expression. So 3 means 3 constants plus variables plus operators. It's like basic definition of complexity, completely arbitrary, but just like, we just chose one. So as you add more complexity, you get more accuracy. So what we then want to do is define this accuracy complexity trade-off. We didn't make this up to get it working. It's like it's been around for a while. Basically just tells you like, for this complexity and this accuracy, like, does it have a good bang for its buck? Now you'll see the equations. The blue one is Newton's law. So this is Newton's law of gravity along the x direction. So it's constant times mass times x divided by r cubed. Now there actually is one that's more accurate. So if you add a constant, you actually get better accuracy, but the trade-off is just like really bad. So like, yeah, so this basically gives us Newton's law of gravity. Of course, we already know it. This is kind of just a test that this pipeline works. Yeah. So like the neural network has learned some function that looks like these symbolic equations. So how does the neural net find it, or how does the symbolic? Oh yeah, gradient descent. So you do like this mixed genetic algorithm with constant optimization. So it can find like really nasty small constants. But you also have to realize, so we fixed the mass scale to be 1 for the mass of the sun. So the constant is actually not that bad.
Okay, yeah, that makes sense, because the step size for regression.
Yeah. So, okay, so now what we do, we take that symbolic equation, we literally rip out the neural network and put the equation back in. Then we test it. Another Blender video that took me like way too many core hours. Okay, so it looks better, but there's still this error, right? Like on Mercury, it's pretty bad. So, okay, so we were thinking about this, like, okay, it's literally Newton's law of gravity. Like, why is it not perfect? And remember, we're learning the masses. We're learning the masses and the force law simultaneously. So we have to check the other one, right? We've got to check the masses. So we look at the masses, and a lot of them are actually really bad. So the planets, like the big planets are pretty good, right? Jupiter, Saturn, the truth is in blue, the predictions are in red. Those are pretty good. But some of the planets are completely wrong. So the different dots are basically different runs of the experiment. Like you just rerun it and you record what the values were. Some of them were pretty bad. Like look at Mercury, it's terrible. It's way under predicted. The moons are all over the place. And so like what happened was, since there's only 31 examples and neural networks are crazy expressive, the neural network is basically learning like a modified version of gravity that works for it, because like it has its own lookup table of like predicted mass and like actual mass. So it's like learned a force law that works for it, but it's like it has like a different definition of mass, basically. Like it's learned like a custom gravity that works for it. And like this is a problem with neural nets. They're so expressive. Now, the reason it did this is because there's only 31 examples of mass. Like if we had 1,000 different masses, it would not have done this. Like it would be way too hard to learn a custom mapping. Because there's not many examples, so it learned this weird function. Okay. What? How many? So 30 masses total that it has to learn. Because we just did a cut, random, arbitrary, 10 to the 18 kilograms above that. I mean, this is real data in the solar system. So we ran this on simulated data before. You generate like 100,000 different masses and it works. But it's like here where you have real data, not many examples, then it's like learning weird custom functions. And that's the problem with neural nets. It's like they're so expressive. It's a good thing and a bad thing sometimes. Yeah. So, okay, how do we fix this? Well, we have this equation that we put back so we can just re-optimize the masses. Because now it's literally Newton's law, we just optimize masses. Okay, so yeah, so we do that and it works. So now it's fixed. I mean, this is like, it's kind of obvious it should work because it's literally just Newton's law and you're like optimizing the masses, but it's still, the pipeline is automatic. We could have found some other property with the, like, we're just using this automatic pipeline. So I think in general, when you do this symbolic distillation, you should replace a piece of your network and then retrain the rest of it. Replace another piece, retrain. Yeah.
So are you like scientists going in and saying, "Oh, okay, that's the right one," and then optimizing it, or is it just saying, "Okay, let's our best equations and then optimize it"? Because that makes sense. Like optimize the entire process.
Yeah. So I showed the this accuracy complexity trade-off. So that one does give us the right Newton's law here. We didn't try the other ones. I think we might have actually. I don't remember, but like in theory, this is automated because this is a known metric that people use. I mean, this metric is like it's bullshit. Like it's arbitrary, right? But it's like it's what people find works well in previous applications. You basically look at, okay, like if I add like a little bit more complexity, the error drops, then I know this is a good equation. That's kind of how the metric works. Yeah, okay. Yeah.
So here you are finding one parameter that is different for lines. So depending on there was one that really affected the equation, like you math, something that very new.
Yeah.
But I do a lot of work in like biology where I'm trying to find information, but I also don't know how many parameters.
Oh yeah, that's good. Yeah.
Definitely varies between individuals.
Right.
So how would you put that?
Yeah, that's a great question. So we did this other example in the original 2020 paper where we don't know the dimension of the force law. So we start off 100-dimensional force law. Then we turn on an L1 norm in the optimization objective. And that sparsifies the force law down to 3 dimensions, which is the correct number. So I think if you don't know how many properties matter, I would set these mass, but they could be like any parameter. Set those parameter values to like 100 dimensions. And then when you're training it, you have your prediction loss and some sparsity loss. And so it should kind of like choose the number of properties it wants, I think. Yeah. Yeah. Okay. So we re-optimize, it works. And we look at the masses and they're pretty good. Like all the planets are correct. Some of the moons are bad. So Hyperion, the moon Hyperion, moon Phoebe those are both bad. They're over predicted. But if you look at like how much influence they have on other moons and planets, it's like so small that you can't do that inference. So it's kind of like, it's reasonable. You get this nice curve from like air to gravitational influence. So it kind of makes sense. Okay, yeah, I'll just like, so yeah, I mentioned the turbulence thing. We're trying to figure out what this network does. Yeah, we have like some initial results. So this is like the neural network on top, symbolic model on the bottom. It does okay. And I think this kind of approach is really nice because once we have this symbolic model that approximates our neural network, we can go back to the theory and actually do some theory development, which might generalize much farther than the neural net. So that's like, it's like a turbulence example. Okay, summary, we as scientists, we should use deep learning to find new insights rather than just make black box predictions. I think you can do this by structuring ML kind of similar to existing scientific frameworks and interpreting them with, say, symbolic regression, program synthesis more generally. And I think there's a lot of exciting future applications. Okay, so with that, I'm going to conclude my talk and let's do some coding. Sound good? Okay. Or maybe should we take coffee? Oh, coffee. Question? Any questions? Yeah.
So one question about the training data.
Yeah.
Is it standard for simulations or is it experiment?
Oh, it's real data. The data we use in the Newton example is real. That's like real data. I mean, obviously this is like a simulate, like this is visualization, but the data is real. The previous what? Which one? Or you mean the other paper? Oh. This is simulated. Yeah, all simulated. Without noise. Yeah.
What are the approaches to make sure complexity sense that we so graph?
Yeah. Yeah, so like, okay, I'll say first, there's no universal definition of complexity. It's all arbitrary. If someone tells you they have like a universal definition of complexity, it's like they're a liar. Like there's like no way to define complexity. So I think the way we kind of like intuitively think about complexity is in terms of how simple is this idea to represent in the basis of my existing ideas. But those existing ideas could be anything. Like if I explain multiplication to someone who's never heard about multiplication, it's like very complex to them. But to me, it's simple because I'm kind of used to it and I've used it in many different examples. And maybe it's like useful for describing my universe, but it's like, yeah, the complexity is arbitrary. So the way I think it's useful to define it in physics is in terms of the frequency of different operators, maybe. So like the way complexity is defined here, you just count the number of nodes. It's like 1, 2, 3, 4, 5, 6 nodes. So it'd be complexity equals 6. Again, very arbitrary. So like Kolmogorov complexity is one way to do it. And that's kind of like formalizes the notion of like a basis of existing ideas.
So do you have a comparison between like specific the underlying model that you're trying to, let's say you learn your proximity to the model.
Yeah.
So you have this comparison.
Of the complexity of the neural net?
Yeah.
I mean, like I guess you could count the number of operations in the neural net, but it would be really big. We've never like looked at that because it's just like so complex. Like I think that Newtonian example is probably like 1 million parameters or something. So it's like complexity, I don't know, I guess like 2 million complexity. that answer it? Okay. Okay.
So what question is, how do you see neural networks fitting into the science? Because you could do this end-to-end, like for example, in
Yeah.
this case, that the gravitational fields.
Yeah, so the fundamental reason you'd want to use deep learning still is because neural networks, you can train them in 1,000,000 steps. Symbolic regression, you can train them in 1,000,000,000 steps. So you want to use a neural network if the loss function is expensive because you need to evaluate it fewer times. Then once you have that neural net, you just record the inputs and outputs, and then you just do mean squared error regression with symbolic regression, which is very fast. So you're essentially using the neural network to kind of transform it into an easier problem for symbolic regression. Now, there's also the combinatorial aspect about it. If you use neural networks to kind of break the problem into pieces like this, normally what you'd have to do is if you're considering 10 to the 9 equations here and 10 to the 9 equations here, you do a full symbolic regression pipeline considering 10 to the 18 equations total. But if you do it with a neural net first and then split it, then it's only 10 to the 9 plus 10 to the 9. So it's 2 times 10 to the 9 equation total. So you've kind of reduced it by square root. You've factorized it.
So is this something that somebody has to do? Like, yeah. Like segmenting the problem into two problems.
Yeah. So the paper. So that's this paper. That's kind of where we did it. So the graph network is like 2 neural networks. It's like a node function and an edge function. And then you kind of like learn the equation for both, and then you get, so like the edge function is this piece, and then the node function is this piece, and you compose them together with like a sum pool in the middle. Yeah. So it's like factorizes it. Yeah.
Okay, and the factorization somehow follows the notified.
Yeah. Exactly. Yeah. 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 Yeah, that's a good question. No, we didn't, but yeah, maybe we should have. Yeah. Yeah. Mhm. Right. Yeah. Yeah, I see what you're saying. Yeah. So like discovering new operators, or like if you're trying to like discover equations for like biology, which is like very limited compared to physics. Yeah. Yeah. I mean, I totally think so. So like one thing you might do is like if you use the normal basis set of equations from like physics, maybe you might start finding that a certain pattern emerges in the equations you discover, and you could just like write that down as a new operator and then just start using that operator on other things. So it's kind of like building up a language as you go, maybe. But like at the end of the day, you kind of have to start somewhere. And then, yeah, I guess like if you see a pattern, keep repeating. Yeah, you could do that. Yeah. Yeah, totally. Yeah. Okay. Yeah.
So often in the data that are features that are very strongly correlated. Is
Mhm.
there any notion differentiate between the two models that have two variables that are strongly correlated? Okay,
I see. beyond this. So like, so I mean, so are you asking like could you assign different complexities to different features? Or like, so, okay, one thing I played around with, and this could be like a fun project because I didn't push it too far. But one thing I tried was I defined the complexity as literally the compressed size of bzip, the compression algorithm, like a zip compression algorithm. So if two variables are highly correlated and the genetic algorithm starts like using one of them, that compresses better than like using one variable here and one variable there. So actually that would be rewarded if it chooses one of the variables. I don't know if that answers it. Yeah. Yeah.
So I'm thinking that we have
Mhm.
So basically, this would be so basically you add enough neurons, so you
Mhm.
so I think you compare this electric approach and say a question or other ways of proving, like what I mean, you have the underlying feature model.
Right. Yeah.
And that you minimize by putting over other ways of expression.
Yeah.
Would it be smaller in the with respect to the
Oh no, it'd be much bigger. It'd be much bigger than the equation.
would be much bigger?
Yeah. So so this, people have basically done this. It's called Equation Learner. The paper is by Sahu et al. 2016. They have this neural network, but the operators are the activation functions. So like if I have like sine, cosine, plus multiplication, they set those equal to the activation functions. So actually the neural network is like a massive equation. Then what they do is they train that neural network with sparsity regularization. And that's basically the equation they get. So it's called Equation Learner. It's a really nice idea, but it doesn't work in practice. And the equations they always get are like way too complex. So actually like a genetic algorithm will find a much more concise expression than trying to do it with sparsity and pruning. It just like doesn't really work as well. I mean, I think it's a nicer idea and it's like very elegant. It's just like practically the genetic algorithm will beat it. Yeah. Okay. Yeah. Yeah. The so I mean, like I typically only go up to like 5,000 data points. Like more than that just won't change the result because like it, and that's like up to complexity of like 80 or something. Like it's just not expressive enough to overfit to more than that many points. I mean, it also depends how much noise you have. But if it's like noiseless, you could do like 1,000 data points and you'll like never overfit. Yeah, unless you have like a lot of features, then you might want to give more data points. Yeah. Yeah, that's a great question. So actually, so one of the old packages, which is now like proprietary and costs $1,000, I think it actually had a probabilistic version. And so the way it works is some of these variables, you actually treat them as random variables. So like maybe Z, is there any others? Wait, okay, pretend this one is X, pretend this is X, okay? And X is like data, and then Z is like a noise variable. And then your loss function would be like the KL divergence between distributions. So that's something you could add in the loss function. And so Piser lets you write like a custom loss function in Julia. So you could totally do that. Like have like a, I don't know, like any optimal transport style loss. You could definitely do that. I think that'd be interesting. I don't think anybody's done that before either. So it'd be cool. Yeah. Yeah, so there's a paper actually last year on proving that symbolic regression is NP hard. So it's like it's difficult. Is that what you're after? I think it's by Marco Vergelin. If you want to look it up. Yeah, I mean, if you have like, so if you train like a transformer to kind of memorize data to equations, obviously it would be like instant, but those don't generalize well. So genetic algorithm is like NP hard, like polynomial time. Okay, and feel free to ask questions throughout, and we could start the coding now. So maybe we'll start a bit of coding and we can get coffee a bit later. What? Water. Oh, okay. Yeah, water's good too.
Yeah, we can have a small break.
Okay.
You guys can start installing.
Yeah, good idea. Yeah, so the tutorial is here. If you want to go to it. So it's I'll paste it in the Zoom as well. Yeah, so it should be like kind of self-contained. So if you start building now, we could come back after the break maybe and start working through the code. So the tutorial is going to walk through like basic symbolic regression with noise, multi-output symbolic regression, custom operators. There's one example which defines like this really complex function to find a relationship on prime numbers, which I like. And then at the end, we'll do deep learning distillation. Okay, how long should we have a break? What do you think? 5 minutes? Really? That short? I don't know. Okay, maybe 10 minutes or longer? 15? Okay, yeah. Yeah, 15 is good. Okay. Yeah, the Colab is, if you go to the main Piser page, there's a Colab notebook and it's the same one. And you just scroll down, there's a Colab button here. Just click it. It'll walk you through it.
What you say is not pretty
It does work. And this will be faster for the deep learning part, but Colab, they don't have, like their CPUs kind of suck. Their GPUs are good, but their CPUs suck. And Piser's a CPU algorithm. So Docker might be better for the deep learning parts, but Colab is better for the deep learning. Yeah, Docker is better for, I need a break. Docker is better for the CPU. Colab is better for the GPU stuff. Okay. Yeah, and I'm happy to help if people have like issues installing stuff. I can help during the break. Cool. So maybe, yeah, so I want to see who's using Colab, who's using Docker, and I'm going to use the same thing. So who's using Colab? Okay, who's using Docker? Okay, so, okay, I'll use Colab for now, but it's like pretty much the same thing. Okay, so maybe some of you have already started, that's okay. So yeah, you do file, save a copy and drive. Now it should already work, but you should have the GPU hardware accelerator selected. Actually, I'm gonna full screen this. Okay. Now, one weird thing that you have to do is you have to use a fallback runtime, because in the last month, Colab updated their runtime and it like broke Julia. So you got to use the old one. This took so long to debug, but it works now. Okay, so yeah, I try to put like bold and then warning. Yeah. Oh well. No, I do the same thing. It's okay. Okay, so you click on the command palette, use fallback runtime version, then say yes. So this is going to switch to an old version of the runtime that still works with Julia. So they are patching it right now. It's just like the current version doesn't work. Okay, cool. So initializing, blah, blah, blah. And then, so you run this cell, it's going to install Julia. It's going to install Julia 1.7.2. The more recent versions, I think there's some other issue with Colab. It's hard because like Colab is built for Python. So like some of these other libraries have issues sometimes, but it's working on 1.7.2. Okay, so this is just going to install like a PyCall, which you use to pass variables back and forth. Okay. And then after that, we're going to install Piser, which you can get off pip or you can get off Conda. We're also going to install PyTorch Lightning, which is going to be used later on in the tutorial when we do some deep learning stuff. So these steps aren't usually required. In Jupyter, you kind of have to mess around with the output streams because it's like you're going from Python to Julia and then trying to print to Jupyter. But I usually use it from IPython, and it's like it doesn't matter. Okay, so that's going to start Julia. Then we're going to install Piser. So Piser's already like pip installed. This step just installs the Julia libraries that it needs. And yeah, so I'll let that run in the background. So let's talk about the first example. We want to just find this simple data set. So it is 2.5 times cosine x3 plus x0 squared minus 2. So we're going to generate 100 points with 5 features. I'm going to zoom in actually so you can see this. Can you see that? Okay, cool. So only 2 of the features matter. Hopefully it won't use the others. And then I'm going to set that to evaluate once it's ready. These are going to be our default Piser parameters. So let me describe them. So procs here, this is basically just how many threads you want Piser to run with. You can have more than one population per thread. It's just going to be a bit delayed. So normally I actually use populations that are at least double the number of cores. So that way one core is always warm. I'm going to set model selection equals best. This doesn't actually affect the search. It literally just it displays the equation at the end. So like best will just look at the kind of bang for your buck in terms of accuracy versus complexity and pick an equation, but it doesn't affect the search. You could change that later if you want. Okay. Now, the n iteration parameter, that's basically the number of steps. So if you've used like SciPy optimized, it's like the number of steps. Now, a tricky thing with Piser is that it's a genetic algorithm. Genetic algorithms don't typically converge. So in practice, like if I'm running a big search, I would set this as large as possible and just quit when I run out of compute or something. Or when I sense it's kind of converged. For these little searches, you can just set some step size. Now, another tricky thing with Jupyter is that it doesn't actually let you stop the search early. So, but in IPython, you can stop the search early and it'll cleanly return the equations. But in Jupyter, you kind of have to restart the notebook if it's taking too long. So it's kind of pre-compiling all the libraries. Should start soon. Okay, so for the binary operators, we're going to use plus, multiplication, and then unary operators. So those are the operators that take one input: cosine, exponent, and sine. You could also write just like plus and multiplication if you want. It doesn't really matter. Like you can pass any Julia function you want, so long as it's defined for your types. So later on in the tutorial, I'm going to show you how to write a custom Julia function and actually use that as one of the operators. And you can get like pretty crazy with the operators. Like, does anybody know that that piece of code called the fast inverse square root? It's like, you know it? Yeah, it's from this video game Quake, and it's, I want to find it. Fast inverse square root. It's the most ridiculous piece of code you've ever seen in your life. So you're trying to compute this thing, right? Like 1 over square root x, and the code looks like this. So it's like a float, and then he defines like an I, and he has like all these constants, and then he does floating point hacking, and like the comments express the feeling, and it's just like some nasty number. So this is the fastest way to compute the inverse square root. So actually, I found this with Piser. And so the way you can find it with Piser is you can define operators that that actually convert types and then convert back. As long as you convert back to a float at the end, you're good. So you can actually find this function. Like you can find this code with Piser. So you can define like some really crazy operators, and it'll just like search with them. Yeah, I think mine's still installing. I should have ran it earlier. Whatever. Okay. So when it gets to there, it's going to run a search. The first execution is going to be a bit longer because it's Julia based, and Julia does just-in-time compilation. So the first run, it's going to start compiling all of the various search functions. Okay. The CPUs in Colab so slow. Okay. Actually, while we're waiting, I'll show you the documentation. So if you go to the Piser GitHub, so my name / Piser, there's a documentation page here, and you can look up the reference for different operators. So there's kind of like so if you want to define like the search space, you can go here, search size, and it explains all the different options. Objective. So there's a lot of different losses you could use. These are the model selections. There's a bunch of different ways you can work with complexities. So I'll talk about those a bit. You can get pretty crazy with the constraints. So the normal constraints, these basically say, I want to constrain the complexity of the argument of an operator. So this is because I was using Piser, and it keeps like nesting like power laws inside of itself like over and over and over again. And it's like you can express so many functions with nested power laws. It's like ridiculous. So what I did to kind of fix this, I mean, like it's like those are valid functions and they fit the data well, but they're ugly. So constraints is a way to kind of disable that. So you say pow this, it basically says the first argument can be any complexity, -1. The second argument, max complexity 1. So it's like just constants. And that ends up being really useful for constraining like low complexity, but still uninterpretable equations. You can also do nested constraints. So another thing I found is that it starts like spitting out cosine, 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 cosine x, and it's like it's actually like a good fit sometimes, but it looks ugly. So so you can disable that with this. So you say like cosine. This basically says inside a sinusoid, I want there to be no cosines. And then inside a cosine, I want the depth of cosines to be 2. Yeah, you can. Oh, those are really cheap. Yeah. Oh, yeah. So I actually generate and check them. The checking is really fast. Now, there is a problem in that if you disable the search space a lot, it can actually kind of handicap the searching, because sometimes it'll start cosine cosine x and then it'll switch it to like cosine exponent x, and maybe that's like the true result. So like having these intermediate expressions can actually help the search sometimes. So you don't want to constrain it too much, but like some of these are actually pretty useful. It really depends on like the operators and how you want to define complexity. Because I think you should define complexity based on what would be interpretable to you. And that's how you want to play around with these things. Okay, cool. Did it run yet? God, it's still compiling. Okay. You can also, so this is another, so I mentioned the complexity is defined as just counting the number of operators, constants, variables. You can also change that. So if you introduce like a really ugly function, like you have an if statement and it starts like using if statements everywhere, you could also define an if statement to have a higher complexity. So this would say sinusoids are 2, they cost $2 plus cost $1. And I think like sometimes it really makes sense to do that. If you have like some really complex operators, you want to make those less. You want to not reward those as much. You can also do that for constants. So this is useful if you want to find an equation with just integers and no real constants. What you can do is set complexity of constants to like 100 and then pass features for each integer. So maybe you pass like one of the features you pass is like 1, 2, 3, 4. And so if complexity of variables is 1, complexity of constants is like 100, it'll actually give you equations that only have integers in them. Yeah. Any questions about those? Okay. Parsimony. This is in the loss function. Normally you would have mean squared error against your data set. You also have this term that is parsimony times the complexity. So you basically want to set parsimony to around like an order of magnitude of what the best equation prediction loss would be. But this is like a very tunable parameter, and it really depends on the search. Sometimes you want to set it higher, sometimes lower, but this can affect things a lot, how you define parsimony. Yeah.
You have, like in reality, you have two objectives. One is getting the mean that we see, and the other one is minimizing complexity.
Yeah.
So you could frame it as a multi-objective.
Yeah. Yeah.
Have you thoughts? Do you have any thoughts about it?
So yeah, so it basically is multi-objective. The nice part about it is one of the objectives is discrete. So what it basically does is it just stores the best equation at each complexity. And then afterwards, you can make that selection. Yeah. So afterwards, you can look at your equation list and say, okay, I want to choose these as the multi-objective objective. But the search itself is just going to explore all complexities allowed. The parsimony sets like how it uses the complexity during the search, but ultimately it's going to give you all complexities, and then you can choose after. Okay, so it's actually running now. That's good. Okay, so the first run is going to take a bit longer. So I've defined plus multiplication, cosine, exponent, sine to try to fit this expression. Okay, I'm going to go back to here.
So I have a question
Yeah.
on your side. So I noticed in the notebook, the default options, you have 30 items set.
Mhm.
You're only using 4 for service.
Yeah.
So is there like a reason to use? I thought like the different items were only for like multi-threading and
Yeah.
processing. Is there a reason for why we're using more items in those formats? Like does that?
Yeah, it can kind of split it. Like if you had like one big population, it actually performs worse than if you had two populations evolving independently on the same core. So you're kind of like, by splitting the population into small groups and letting them evolve independently, you're kind of letting them find like weird evolutionary branches
Right.
that otherwise would just die out immediately in like some larger group.
Okay. So it has more to do with like some of that matches and like the genetic algorithm
Yeah.
that like has to do with CPU.
Yeah, I mean, you definitely want to have like more populations than cores,
Right.
so that it's always warm. But it also like helps for the actual search itself. Yeah, yeah. But yeah, let me see. So all of the parameters on the reference page, these are all tuned by this big hyperparameter scan I did. But you can tune them for a specific problem and probably get better results. So you'll see like the mutation weights are like very specific. It's literally just because I tuned them on this kind of benchmark data set. But you can play around with them according. So for example, like maybe, I don't know, like maybe you think your equation is like really weird and it's not going to find it normally. So you want to increase like the randomization weight. Or maybe you find it keeps getting like unsimplified equations. So maybe you increase the weight simplify. Oh yeah, so this is like the crossover probability. So this basically says 6% of the time, 6.6% of the time, it's going to do a crossover rather than a mutation. So you can increase that, decrease that, whatever. These are all like hyperparameters. Even I don't really have like intuition for these. It's really like you just play around with them. So I have a one. So if you use weights and biases, I have a weights and biases here that is kind of like what I use for tuning. And so you could borrow this if you want. So there's like a sweep file here that you could play with. So it's just Piser _1db. Okay, so it finally ran. Cool. Okay, so now that it ran, you see like during the search, it'll print out equations over time. So this can be useful if you're watching it and maybe you want to stop early. So if I just enter on the model, it's going to print out the equations. So those equations are actually a pandas data frame. And so if I do model.equations, oops, my fingers are getting too fat. Okay, if I do model.equations, it's literally like a pandas data frame, and then I can do like so if you've used pandas, you can do like .query, so like loss less than, I don't know, like 0.1, and then it's only going to show me the equations matching that query, and then I can get the strings with .equation, and it's going to return the equations. So yeah, so that's a pandas data frame you can query. Now, we can also view the SymPy format. So if I want to look at a pretty format of the equation, I can do model.sympy. Now, by default, it's going to return. So for all of these functions, it's going to return the one specified by your model selection strategy. So if I run model, it's gonna see this one, it highlights this particular row. That's like the pick of the model selection strategy. But in actuality, what I can do is this model.sympy, I can actually, so if you do model.sympy question mark, it's going to show you the help page. And you see there's an index parameter. So that index, I can pass the particular equation I want. So maybe I want, there's too many columns. So I'm going to filter this to complexity, loss, and then equation. And maybe I like, yeah, I like this one. So row 6. So then I can look at row 6 and get the sympy of that one. Yeah. Oh, that's a good idea. No, sympy is just like the post processing. So all of the search is done in pure Julia. It's just kind of like given to Julia. Julia runs for however long and then returns. It uses this library called Symbolic utils for simplification. And you can define custom simplification rules. So for example, this is how you write rules in that language. And so you could define custom rules like that. In practice, I actually find simplification doesn't help that much because it's trying to optimize the complexity, and actually it'll just like end up simplifying it anyway. But you could define explicit rules like that. And yeah, I mean, some searches, they might help a lot depending on the rules. Okay, so yeah, so you can define like whatever row you want. You could also get LaTeX. So model.latex, we'll just print the LaTeX. So again, it's the row selected by model selection, but I can do a specific index to get the LaTeX for that row. Now, if you want to evaluate your model, the equations in Python, you can do model.predict. So this is scikit-learn style. So you do model.fit x, y, and then model.predict x. And you'll see here, I actually have a second parameter in the predict function. That is the index of the equation. So if I want to predict with the 6th row, I can do 6. Maybe I want this one to be like the first row. Right? So now I'm like evaluating a specific row. So maybe I want to, I don't know, maybe I want to plot this. Or actually, I think this one is multivariable. Let's plot later. Okay, let's define a custom operator. So now we're going to write some, like a bit of Julia code. So Julia is largely very similar to Python. The reason I wrote the backend in Julia is just because it's compiled, and I didn't want to write C. So say we want to find this equation, x0 to the power of 4 minus 2. Now say we're working in a specific field where a quadratic operator is like very common. I don't know why, but let's say it is. For this field, we can define a custom operator like this. So this is Julia code. And in Julia, you do caret instead of like times. So it's like a little difference. Then we also define a sympy mapping so that we can turn it back into sympy. So that's basically how you do it. And of course, for binary operators, it would be like this, right? Like XY. You can also put anything. You can put like if statements there. They don't have to be differentiable. You can do type conversions. You can do bit level hacking, evil bit level hacking, whatever. And it'll just compile. It'll go through the simmed kernel compilation, and you'll get like a fast version of that operator. So yeah, so it already found it. I mean, that example was simple, but okay, cool. And then when we do model.sympy, it's going to actually use our operator. that we've defined, which is cool. If we want it in, say, the symbolic form, we don't want it to evaluate it. What we can do is define a custom. So maybe I'm going to call this like Court 2. I can define a custom SymPy function. Court 2. It's like SymPy.function. And then pass, I think. And then I just pass it here, Court 2. I think this will work. And then when I get the SymPy version, it should use that operator. Yeah, so now it's using this operator. Yeah, so now it uses my custom SymPy operator instead of expanding it. Okay, any questions so far? Okay. Now, in terms of scoring, so when you do model selection equals best, this is going to make a selection based on the Pareto front. The Pareto front is, it looks like this. It's the black line at the kind of top right of the picture. So the x-axis is the parsimony, that is the complexity of the equation. The y-axis is the accuracy. And so the black line represents the most accurate equation at each complexity. And so what the score looks at is how fast it drops. So if I get a big drop at this complexity, that is a high score. And that has traditionally been used as a metric, or like, this is a good equation. I mean, like, it's very arbitrary. It's just a metric that seems to work well. Like if you set up some example problem, it tends to pick the best example in the presence of noise. Yeah, it doesn't affect the search. The model selection you choose is just the final output. And you can always just like choose like one based on the index, right? So this is like an over complex equation. Okay, cool. Let's do some noise. Why didn't it render? Okay, so what we're going to do here is fit this model, y equals 5 times cosine 3.5x0 minus 1.3 plus a noise term plus epsilon. Epsilon is drawn from a Gaussian with sigma squared variance, where sigma is also a random variable. So it's drawn from a uniform distribution between 0.1 and 5. Now, what we can do here is weight by the amount of noise. So we're not going to give it the explicit like error, but we can give it sigma. So say we're doing like an observation in an experiment. We know the error, we know the uncertainty. So we can weight the error or the mean squared error by that weight, by the signal to noise ratio. So we could define weights like that. And this is basically computing it. This is what the data set looks like. Okay, so it's very noisy. And at every point we know the sigma, but we don't know the specific direction, basically. So we can define weights as 1 over sigma squared, which is the signal to noise ratio. And when we do the model.fit, we can pass the weights. And now it's going to use those weights in the loss function. Now what we're doing here is we're actually defining a custom loss. So this is target prediction weight. And so we're going to weight the loss by the weight we pass, and then absolute error. Okay, so we can do that. Now, funnily enough, like sometimes with noise is actually better than without noise. And I think that's because the scoring strategy is actually kind of built assuming noise is in the data. Like if you have noiseless data, sometimes the score is like really weird. Yeah.
Where are you mapping from? Like I see that there.
Oh, it's just the order.
That is the order.
So if you pass, like if you pass a weights, it's going to assume your loss function is weighted. And it's going to expect there to be 3 arguments.
Okay, so the name of the parameter.
Yeah, you could define this as like whatever. Yeah.
No, no,
Oh yeah, that could be like whatever.
that's all.
Oh yeah, when you call fit, it's weights. But here it's just the order. I mean, like maybe in the future, yeah, maybe I should do that, like name parameters and loss. That's probably better actually. It's a good idea. Then I could do like this maybe. Oh, that's a good idea. And then you could pass like arbitrary additional variables. Oh, I like that. Okay. You gave me an idea. Okay. Yeah, I like that a lot. Okay, cool. So yeah, it's fitting. 235 iterations. Done. That's still fitting. I think we actually might have started Julia. I think we started it with only 1 thread. Oops. Okay, let's just plot this and I'm going to restart Julia with more threads. Okay, it's almost done. So yeah, so this Pareto curve is like much more typical. You kind of have like, once it finds the true equation, then there's like a smooth, and that's just like overfitted rows. So yeah, so it seems to pick like here, and then you see the scoring of these is like really bad. And that's because it's just like overfitting to noise. So we can plot this. Let's look at the plot. Yeah, so it's pretty good. And that's because we're doing complexity regularization. I mean, like it's also a lot of points, but it's good that it can like fit with noise. Okay, I'm gonna restart the notebook because I want to launch Julia with like 2 threads. Actually, how many cores do these have? Does anybody know? Oh, it's four threads, right? Is that? Yeah, I don't know. I don't know what the different runtimes of different cores. Okay. Okay, so there's 4 threads. So I'm going to restart my runtime. So runtime, restart runtime. And then in this line, so this is like when I turn on Julia, I'm going to say threads equals auto. And then I'm also, yeah, I might as well say optimize equals 3. So it's going to turn on like heavier optimization. So that should make it faster. So the auto is just going to choose like an arbitrary number of cores. Any questions? Oh, we wait. Okay. The next example. Okay, so this example is just multiple output. It's pretty straightforward. Like it's just not gonna. Oh, I forgot to run the whole import thing. Where's that? So if you have multiple outputs here, so you see this is y1 equals, or I guess like y0 equals 1 over x0, y1 equals 1 over x1. Like that's what this equation is. So if you pass in multiple y features, it's just going to fit different scalars for each one. Like it doesn't do a vector search. And so Alan asked a question about this earlier. And I think in the future it could be possible to do like vector searches, but right now it's just easier to have like a bunch of different scalar searches. It will batch the equations together. So if you have like multiple outputs, it'll kind of search with them simultaneously. So it'll rather than kind of restarting the search for each one, so it'll be faster. Okay. So we have 2 more examples left, and then we can conclude. So yeah, once this runs, so this next example, this is my favorite example, I think, because we're going to install a Julia package and use it in an operator. And this was like really annoying to get working, but now it's like it's nice and it works well. So we want to find this relationship. Y equals the 3x plus 1th prime number minus 5, where x is the input. So to do this, we're going to use the primes.jl package, which gives us basically a list of primes. So to get that, we're going to install primes.jl. So this is like the equivalent of pip install for Julia. So that's going to install it into the Piser environment, basically. Package.add. Yeah, Colab CPUs are so slow. I promise this is faster if you run it on your desktop. Piser is not slow. Okay, and then once that's installed, you import. So it's same as Python, import. Then what we do, so when you run jl.eval, it's literally just passing this code. It's passing that string to the Julia runtime. So you can run any Julia code you want in this string. So this first line imports primes. This part is going to declare a new function in the global namespace of Julia. This function is called P. It takes I as an argument, where I is type T. So T is whatever the input type is. It's basically just going to record that as the type. Now, this is an if statement in the operator. You can have if statements in the operator. This first line says, if I is between 0.5 and 1,000, return the prime number. So first it's going to round, because we're dealing with real scalars here. So it's going to round to the nearest integer, compute the prime number, and then convert back. Now, if it's a negative number, or if it's like too big, it's just going to return a nan. So if you have a custom operator, you can just return a nan if it's out of bounds, and it'll just throw out that equation. We want to do that here because if you're computing like the 100,000th prime, it's expensive. And of course, negative primes don't, there's no negative primes. Okay. So this search is running. So you see, like when it has multiple outputs, it just prints them all out. With multiple outputs, basically all of the previous commands become lists. So dot equations is now a list of pandas data frames. So model.equation 0 would be the 0th output is a pandas data frame. When you do .sympy, you pass a list of what equations you want. So maybe I want the first of each output. And you would do the same with .predict. Right? So it's like, this is my list of indices. And of course, that is the correct answer, I hope. Oh, wait. Yeah, Okay, good. Okay, so let's, wait, did this already run? Okay, it ran. So this is defining a function P. Now we can actually call this, because we have this Julia runtime, we can literally just call jl.p, and that is our function P, which exists in Julia, but we can access from Python. So I can pass like a number like this, jl.p of 2, and it's going to return the second prime number. So you can test functions from Python. If I pass a float, so let's say I pass 100.0, which is a float, it's going to, so t is going to be a float, and it's going to convert to an integer, compute the prime, and then convert back to a float. So you can see, okay, good. The same is true if I give it a scalar value that's not exactly at an integer. You can see it rounds to the nearest integer, then it computes the prime, and then it goes back. Of course, if I give it a negative number, it's going to give me a nan. Okay, cool. Okay, so now that we have the function, we're going to generate some training data. And when we declare our Piser regressor, we're literally just going to pass in the name of that function. So if you've like loaded some library, you can just pass the function in here, or if you define a function, the same thing. So the SymPy function, we're just going to not worry about SymPy expanding it, just call it SymPyP and declare the function. This might be a bit large, so you could like make this, I don't know, is 10 going to be enough maybe? Let's see. And that is going to compile our custom function into that search loop, simdify the kernels and whatever, and then search with that. Yeah, I don't know how long this is going to take, but I can move to the next one. Yeah, so that's P of 3x plus something, minus something. Okay, there it is. Cool. I think that's it. I mean, the loss is good. Yeah, 3x plus something, and then it's going to round, and then minus 5. So it found it. Like that is the prime number relationship that we were looking for, which is cool. Like the point of this is that you can define any operator you want, any loss function you want, and optimize a symbolic expression. Okay, this last part of the tutorial, we're going to look at that symbolic distillation idea. Let's say we want to learn this relationship. We have a time series xi x sub I 0th feature, and then xi sub 2nd feature. Okay, so this is like t comma feature. Now, every element of the time series is going to be mapped to this function yi. So this is like at every element we map to yi, then we sum that. So we take an average over our time series of that quantity, and then finally we're going to square it. Okay, so if we did this with pure symbolic regression, I mean, I don't think it's too bad, but it'll be much easier if we break it down with a neural network first. So that's what we're going to do. We set up our neural network inductive bias like this. Z equals f of sum over g of xi. So every element gets passed through this neural network, which then is summed over, gets passed to another neural network. Now, I'm actually going to hack this a bit. So I realized that 100 is probably way too many time steps. So I'm just going to do this 10. If you already ran it, sorry, but I'm going to make it 10. Because I realized like we're averaging a cosine over 100 like random numbers. So it's just going to average to 0. So I'm going to do 10. Let's see if that works better. Okay, so that's my data set. Generate the data set. Now, this is the neural network. I don't know, Omar, what did you teach? What language did you teach? PyTorch? Okay, cool. So yeah, so this is just like a simple multi-layer perceptron with ReLU activations. We're going to define a function G as an MLP, function F as an MLP, and this inductive bias is literally this. Like we just wrote this as a PyTorch module. Okay. Does that, yeah, please ask question if it's unclear. So if you've never used PyTorch Lightning, it's basically a way of easy training of PyTorch modules. I really like it. PyTorch Lightning, you basically, the training step and the optimization configuration are part of the model, which to me is kind of more intuitive. And it also does all the kind of data transfer stuff. Okay. So we create the data set objects, and now we're going to train it. So this is going to use the GPU if you're using the GPU runtime. The benchmark equals true. That's just a hack to get more speed out of GPUs that PyTorch Lightning gives you. Okay. This is the .fit. So this is just like a normal PyTorch training, but we have a very specific inductive bias that we're going to fit through. How many steps did I do? Okay, so this is 50,000 steps. So one thing to note is that here I've actually defined the dimensionality of the space. So rather than summing like a vector over a sequence, I've fixed it to 1. Like I have a bottleneck. In practice, it's actually better to start at like 100 dimensions and then sparsify that space during training. There's this cool paper called the lottery ticket hypothesis. I don't know if anybody's seen that. Basically, the reason, so people think the reason wide neural networks work better is because you basically have more lottery tickets, and one of the functions, so like every different pathway through the neural network is like one function, and the wider the network, the more functions you start with. So it's kind of easier to, like rather than having to learn the function, you just like find the function in your neural network. Because it's wide, there's like more functions to pick from, and you just like select that function. Yeah, basically what I'm trying to say is like, you would normally put this to like 100 and this to 100 and then sparsify it. But we just cheat here and choose 1. Yeah. Yeah, so the loss here is computed like this. Normally what you would do is you would pass this yi here, yi, and then yi, and then you would do loss plus equals torch.abs yi.sum times like 1 equals -6. So that would be an L1 regularization, and that punishes the number of features used by yi. So here we're cheating and we're just using 1, but in practice, it's actually better to start high and then sparsify. So that would be like a L1 regularization. Oh, someone asked in the chat, have you ever tried with L0 regularization? So so there's some papers that, okay, so the reason you can't do L0 regularization normally is because we want it to be differentiable. Like it's a differentiable objective, and L0 is not differentiable. So L1 is the closest thing to L0 that does not have an instability at 0. because all the other LP norms with P less than 1 have an instability at 0. That being said, there are some papers that give you ways of like explicitly fitting for L0 by kind of like slowly going from L1 to L0. I haven't tried them. Like L1 works for me, but I think that's an interesting direction as well.
Okay, thank you very much. Yeah, I very, as you mentioned, I think there is this technique with L0, so I was curious. It's like a hard sampling and sort of we sort of try to make it L0, and I was just curious to know. But if L1 is already working, because sometimes L1 is not necessarily sparser. It should help, but it does not guarantee because it's just L1 regularization. Okay, thank you very much. It's very good to know that it's working.
The paper I'm thinking of is from it's like Max Welling's group, I think in like 2018 or something. I think. Yeah,
there are a few. There was one by Luizos where they tried a hard sampling method, and then there was an improvement on this. But if L1 is working, it's much nicer, of course, because it's very convenient. But maybe L0 will make it even sparser.
Yeah, I want to like try some of these methods. I actually haven't tried any of them yet on this problem, but I think it'd be really cool.
Okay, that's very good to know. I'll follow up by email with something because I've been working on in this direction.
Oh, cool. Okay. Yeah, I think that would be interesting. Yeah. Okay, the loss is going down. Oh no, it's going up. There's like a part of the training loop here. I think it's like one of the mini batches just like screws it up maybe. Oh yeah, because I'm not shuffling the data loader. Okay. Yeah, I'll just let it run a bit longer and then we can stop. Yeah, that really hurts. If you don't shuffle the data set during training, it really hurts. Wow. I'll just stop early. I mean, I don't know how good this is going to be because the loss is pretty bad. So normally you would train the network like maybe 10 more minutes. Okay, so what I'm doing here is I'm evaluating only a piece of the neural network because now I want to fit that with Piser. So I have this test data set maybe, I think this is still the training data set. Then I create, so this is like the input output pairs that I mentioned. So now I have the X and the Y, and I want to give those to Piser and see what it finds. So I don't know if this will work because I didn't train for very long, and I mentioned there was a shuffling issue. But we can see what it gets. Let's see. Now, one thing to note is that there's actually a degeneracy in this problem because the scale in G can be offset by the scale in F, right? And another problem is that G can actually learn an arbitrary additive constant because F will just memorize what that constant is and subtract it out. To remove those degeneracies, YI actually needs to be arbitrary size because then there can't be like a fixed constant. The multiplicative degeneracy, I don't know how to make that go away though. I think we just have to live with that.
So that's a fundamental problem. You have to regularize each component to
Yeah.
negative power.
Yeah. Yeah. So one thing we found in that the force law paper, it's even worse because the first neural network in this, it can actually learn an arbitrary coordinate system because the second neural network will just like invert the coordinate transform. And that's like very problematic. I mean, it's not too bad for us because it's just like, it's just a simple rotation. But if you're dealing with more complex systems, like we could learn like a really nonlinear coordinate transform. So I think, yeah, I think what you said is the smartest approach, just have some L2 regularization there. And that tends to help like reduce the number of degeneracies. Because then it's not like learning like some weird coordinate transform and then transforming back. Because like neural networks, they like doing that. They're evil. Oh, so yeah, so we do L2. Yeah. I mean, so the force law coordinate transform, the L2 doesn't actually help that. That's like still there. But the L2 does make it, it kind of forces it to be a linear transform, which you can still kind of work with. Okay, did this get it? I didn't actually look. I don't think so. Let's see. Okay, it actually got it. Or no, it didn't. It was squared. I don't remember my trig identities. No, I don't think that's right. Okay. So yeah, I don't think it got it there. Wait, that's not the best equation. What's the best one? Okay. So yeah, I think we just didn't train the neural network for as long as we should have. But the point is, like, now we have a way of kind of understanding what the pieces of the neural network has learned, which is a great thing. And I think that's, I mean, both for the interpretability side and for kind of doing symbolic regression with more complex high dimensional data. So we could, so once we find an equation for F, an equation for G, maybe we train it a little longer with a better model. Then we can compose those equations and get like a fully analytic approximation of our model. Okay, so we're at 3:30. I'm gonna stop here. And I'm happy to take questions. And thank you all for joining me. All right. Yeah. Yeah, I started procrastinating my main thesis project, and then this became my thesis project. I just like, yeah, I don't know. I was going to be on this thing called like stellar streams. It's this astronomy thing. But I started working on this because like there used to be this package called Eureka, which was like a really nice symbolic regression library, but now they're charging like $3,000 for it. So I got really pissed off, and I'm like, okay, I'm just going to write one.
Like implemented.
No, but like I feel like it just pissed me off so much that I put like years into this. Like I can't put that on someone else. Like start like it's like yeah, what? Sorry? Oh no, I don't think I can accept one because I'm on a visa. I'm Canadian. I don't think I can accept donations. But thank you. Yeah. Yeah. But yeah, I use it. So like, I mean, some libraries that are maintained by one person, like you get worried that they'll kind of go away. But like, but like I use this, so I think I'll keep maintaining it for a long time. So yeah, so this one is, so the 2006, or not 2006, but like the 2006 archive number. So if you go to my GitHub, that code for that one's here, so you can reproduce everything, and there's like a Colab for it. Yeah. So the Newton example, so that one's not published yet, but when it's published, it's going to be open source. I think it might actually be open source already. Yeah. But it's actually like similar training code to this one. How long is what? Oh, I mean, I think it depends like how good you want the models to be. I think in the final copy, we train like 1,000,000 steps, but the Colab is like 100,000 steps. I think it's like 10 minutes, maybe 10 minutes training. The final example, so the simple particle examples are faster. The dark matter one, that one's more expensive because the data set is like really big.
So I think that is a little surprising in the sense that the environment have this, like they tend to run through quite a long time. I would
Yeah.
think like zero evolution and that kind of thing that entire steps.
Yeah.
It's surprising that they find this complex equations so few steps.
Yeah.
Do you have any intuition why?
Yeah, I mean, I think so. Part of it is definitely the neural net part, and like having this inductive bias that kind of forces it and eliminates the degeneracies. Because so in this equation, you're only doing genetic algorithm on this, which isn't so bad, and then you're doing a genetic algorithm on this, which isn't so bad either. So the neural net kind of splits it into easier problems that you can do symbolic regression on. And I think that's a big reason we're able to find these complex expressions. So I think you could do this one with pure symbolic regression. You just need a lot of cores. And then you could maybe find it. It scales really nicely. Like that's the nice thing about this algorithm that I'm using, tournament selection. Like you could just distribute it over like thousands of cores, and it like improves the search. Yeah, and there's oh yeah, I want to show this too. There's an interactive reference. This is like a weekend boredom project. So this is like a JavaScript automatic reference. So you see at the bottom, there's a Piser regressor object. And what you can do is you can hover over these and it says the documentation. And then you can click on the operators you want and the options you want. So maybe like you want a lot of steps. Maybe you want to use L1 loss, denoising. And you look at the bottom and it generates the, the definition. And it even does it in real time, see? Yeah, okay. I wasted way too much time on that. But there's yeah, the reference page is has a lot more like details on all this stuff. And then if you want to hack the back end, there's also a customization page. So like say you want like a really weird constraint where you want to redefine complexity or redefine I don't know, the evaluation scheme, you can go to this page, the customization page, and it tells you how to hack the backend, kind of like what code to edit. And there's also documentation for the backend as well. So that's SymbolicRegression.jl. And there's docs for that there.
So this one is not yours.
This is mine. Yeah, this is the backend of Piser. Yeah. Yeah, it started as just Piser, but then the Julia people wanted me to kind of like separate it so they could install it in like pure Julia pipelines. So now it's like a separate library.
Yeah, you already asked.
Okay. Yeah, you can use it directly. Yeah. Yeah, the API, like it's not as nice. And I think part of that is like the Python ecosystem for machine learning is like really big. And there's a lot of like really nice API standards. So the symbolic, like pure symbolic regression, it's not as nice to kind of work with, but it's really useful for hacking because you can like change a function in the backend and then just rerun it, and there's like no compilation time. And you can work with like the trees themselves in like the actual tree data structures and like add mutations, whatever. Yeah, and I'm happy to answer more questions. Like if you want to email me, I'm happy to answer questions or post like an issue on the page.
Question?
Question, yeah.
Yeah, for
No,
Zoom.
no rust. There shouldn't be any rust. Is there rust somewhere?
I mean, it was just going for run, but I was doing it over, but I'm not sure what.
Really? Oh,
I'll show you later.
okay. Okay, yeah, there's no rust. Maybe one of the dependencies I added to that Docker container. I don't know. Question online?
Yeah, question. So if say I was interested in discovering a symbolic form to say some differential equation, is there, I guess, two questions. Is there special support for time series data? I guess there's like the issues of compounding errors. So are there like ways to fit time series data with like that in mind? And then also, what if I was interested in potentially like some multivariable operators as well? Is there support for that?
I see. Okay. Yeah, great question. So first question, to work with differential equations, my recommendation is to go to the original paper. Actually, but so in the original paper, we do have differential equations. So we have, where is it? We have some Hamiltonian dynamics. Yeah, so there's like some Hamiltonian dynamics equations. The trick here is you first solve your problem with a neural network. Like solve your problem with a neural differential equation.
I see.
And like you would do back propagation through time with a neural network first. Then take that neural network, which maybe predicts the acceleration or something, and fit that with symbolic regression afterwards. And again, the point of that is, since doing optimization through integration is really expensive, you want to do the expensive part with a neural network, and then the cheap part with symbolic regression, which would be fitting the acceleration maybe.
Yeah, that makes a ton of
That's always
sense.
good. Like when you have a really complex objective, you first do it with a neural net and then fit the neural net with symbolic regression.
Yeah.
Yeah.
Okay.
What's the second question again? Sorry.
It was about multivariate operators, say like matrix.
So you can only do binary operators. So you could like, you could kind of hack it maybe and do, like if you have a 3 variable operator, you could kind of write it as like two variable operators. And then in the evaluation, you would only evaluate if they're kind of like stacked, but that would be kind of expensive. But right now there's only 2 variable operators.
Gotcha. Okay.
In the future, it would definitely make sense to allow arbitrary degree operators. I just haven't added that yet.
Yeah. Yeah, sounds complex. Thank you for answering the questions.
Yeah. You know. Okay. Cool. Okay. Any others? Let's stop there. Great. Yeah. Feel free to email me or raise an issue on the GitHub. I'm pretty responsive on Piser stuff. Cool. Okay. Okay. Thanks, everyone.